Okay, welcome to Chapter 6. This is Module 4, Chapter 6. We will be introducing the total station and theodolites. Chapter 5 was about electronic distance measurement. The book probably should have had theodolites before electronic distance measurement. As we will note, the biggest difference between a theodolite and a total station is theodolites do not shoot distances. They do not shoot distances, and they usually, maybe even all the time, do not collect the data on board. So that's the biggest difference. So we're going to look at this. I'm going to walk through the overview of the PowerPoint and show you some portions of it all, as usual. And so here we are sharing the screen, and we're looking again at your book and the Chapter 6 slide of it all. All right, so some of the things that are done are measurements of angles. We have vertical angles that are measured from two different directions. Let me go back. So a theodolite, and here I'm going to actually stop my share for a second so I can graphically and visually show you how this works. So a theodolite measures angles. It measures angles literally horizontally, this way, as well as vertically. And we've seen a need for vertical angles to be measured, and that need is on a slope. The chain works fine on flat surfaces or level surfaces, or where you can keep the chain level. But if it's too big a slope, you can't keep a chain level. And as we noted in the last chapter, the electronic distance measurement is so much faster, so much more economical, and even more accurate at longer distances. So you have to be able to measure the vertical angle. Surveyors tend to measure the vertical angle with 0 being straight up. Like if you want to think like straight up, or if you want to think north, it's fine, but really straight up. We're talking about a vertical plane that goes up and down like this. So surveyors usually will measure straight up, so that straight out or level, straight in front of you like that is 90 degrees. So now we'll go back and look at the screen sharing, and we will continue. Let me get that for us. We want this one here, and we will begin our screen share. So the types of angles that we're looking for vertically are zenith angles or nadir angles. Surveyors around here, most surveyors in the United States will use who's measured from the horizontal, which is a zenith angle, such that straight up is 0 degrees and straight out is 90 degrees. The book or the slides will continue to show us here. The nadir angle is measured from vertical. The vertical line is being directly beneath you. Older instruments used to measure this right here, this horizontal direction, as 0. Instruments have gotten away from that nowadays, but I have utilized some very old instruments that were theodolites. 0 was right here. Nadir directions, 0 is down here at the bottom. Zenith directions, 0 is here. Most surveyors and every piece of equipment I've had that's more modern, every electronic instrument has 0 measured from up here. So it's kind of important, but you have to understand where we're measuring from. You may get a problem or two that talks about that. Like I said, some of the older ones measured from the horizontal. Most will measure from the zenith nowadays. So meridians. We have ultimately, looks like, sorry, I always go too far. 3 different types of meridians. A meridian is like well, it's how you, like, you think about a meridian is, you know, the vertical lines of latitude that is measured on a, or I mean, sorry, vertical would be longitude. The longitudinal lines that are measured on a globe from the North Pole to the South Pole, you can think of that as a meridian. Um, the angles that are utilized are generally um, geographic or grid. Magnetic is not used so much anymore. And what these are is also, you can think of the meridians as the basis of your coordinate system or the basis of your maps. So a geographic meridian is just what it says. It matches up with the latitudes, or I'm sorry, I always say latitude, but the longitude on the globe, you know, such that 0 goes through Greenwich meaning, or Greenwich, England, and we move east and west from there, measuring until we're on the complete other side of the earth for 108 degrees. So that's a geographic meridian. The magnetic is a little bit different. Magnetic is literally utilizing a compass. Magnetic north poles and magnetic south poles are not true north and true south poles. They have a variation that changes every year throughout the year based on a magnetic declination, and therefore they have their place. They're relatively good enough for navigation. Even that, though, today's modern ships are taken into account using GPS and correcting for magnetic meridians. So, you know, it has its limitations. The grid meridian is what a lot of people use surveying, and that is your state plane coordinate systems. And I'm not sure that we talked much about that, but the state plane coordinate systems allow for the Earth's curvature to be flattened in a plane. And I know we talked about that now in the earlier chapters, but that's the plane that we work in, and we flatten the Earth out and we take into account its curvature and flatten the thing out, and we call that a grid meridian. So there's your basis of measuring angles. Horizontal angles basically have 3 different types of angles that you can measure. They're interior, exterior, or a deflection angle. And so this next slide actually will explain to you a little bit clearer what they all are. So these angles right here, like this, are interior angles. And so in this particular case, somebody's starting here like at A, and they're measuring to B, and they're measuring here on the interior angle. This right here, as the example shows you, is the exterior angle. It doesn't matter which way you're measuring, as long as you know which way you're measuring for certain calculations. And so in this particular instance, we will note that, and I'm gonna skip a couple slides ahead real fast. Yeah, all right, so we're gonna get to deflection in a second. So what we notice here is that these are all interior angles, and there's 5 of them. There's 5 interior angles, 1, 2, 3, 4, 5. What the book talks to you about, and I'll go over it because it's useful information. It's something that you can understand and take something from it. And I know there's a question or two about it on the midterm exam, but it's not something you'll utilize a whole lot of in your construction management. But it is something that's useful when a surveyor talks about things that you might pick up on to have useful knowledge of what they're doing. When a surveyor runs his control loop or her control loop, they're closing out a figure. They're making like a polygram. It's no, not a polygram, polygon, and it's a multi-sided shape. In this particular picture, there's 5 of them. So a perfect figure has a known number of degrees. And in this particular instance, the known number of degrees would be the number of angles, which is called N, and just the unknown, the variable is n. If you're turning interior angles, it's n minus 2. So the total number of interior angles minus 2 times 180. So in this case, that's 5 minus 2, that leaves us with 3, times 180, which is 540 degrees. And if you were to do this right here, it shows you that there's a problem. You come up short by a few degrees, or almost 2 degrees. The next slide, well, not really, but this one comes up short. What you would have to do is you correct all these by equal amount to equal 540 degrees. You'd have to make a correction everywhere. You don't need to be too concerned about that, but do realize that that little formula I just gave you, it's in your book, but we're looking at n minus 2 or n plus 2 times 180, depending on interior angles are n minus 2, exterior angles are n plus 2. And that again it's on page 117 of your book. The next thing is something every now and then, and you could utilize this in construction. This is a deflection angle. So a deflection angle is when you're looking forward on a straight line, and you have a deflection off of that straight line. This is utilized in roads, water lines, even sewer lines, when you're going in a direction and then you have this bend. The 22 degrees in 18 minutes is not a typical bend by anything construction, but things like 45, 22 and a half, 11 and a quarter degrees, all of those are typical deflections that you would find in water line or sewer line. And a deflection simply is a deviation, a deflection on one side or even the other maybe from the straight line that you're on. And it's measured going forward. And again, it's from the straight line here. This is a 22 degree, 18 minute deflection to the right. Going on this straight line, we have a 38 minute 38 degrees, 6 minutes deflection to the left. So that is something you'll run across. I don't think we're going to test much on it, but it gives you an idea of what you're looking at as far as construction goes and the third type of angle that's being measured. This is a quick little overview of theodolites. It's not that important to you, and I will just quickly mention them. These open-faced vernier transits, I have used them. What they were able to do was turn an angle, and then you had to actually read a vernier. A vernier was a plate on the bottom of the instrument, and see if there's any pictures here real quick. No. All right, so it was a plate on the bottom of the instrument that rotated. You rotated around the plate, and you measured, you read, I should say, the marks on the plate. The ones I had to read early on were with the magnifying glass. You actually looked at a magnifying glass, and let me stop the screen share real quick. I literally would take a magnifying glass and look right down on top of the instrument and read the angle. That was the old style open-faced vernier transits. The optical theodolites, I had a couple of them that I worked with. They would have a way of measuring the angles. We didn't have electronic theodolites. They measured the angles, and you could read a plate on the inside of the instrument. You didn't need the magnifying glass, but you read it from the inside. The electronic theodolites would have an electronic or digital display on the outside of the instrument, much like the total station today, but I personally never used an electronic theodolite. I did use the ones with both open-faced and optical theodolites. So let's head back over and create that screen share again. There we go. So those are the different types of theodolites. The book's going to focus a little bit more probably on the electronic one. But when you're turning angles, it says here, angles are read left to right unless you're laying out. The laying out is when you might use a deflection angle. Angles are read to the left to right. That's referred to really as a right angle, but that is how they work out. 0 is usually where you have your initials target, your backside target, and then you turn towards your right and you measure your foresight target. Doubling angles is a method, and let's see here. All right. It's a method that you may or may not use very often. And it can be done a few different ways, but the purpose of doubling an angle is to make sure you get it right the first time, as well as take any error out of the instrument. What you would do normally, you wouldn't, the way this is described is you turn the angle once and you preserve that position, and then you resight it and you turn the angle again, and depending on which way you're turning it, you either have a doubled angle. So if I turn 90 degrees and I want to check myself, my next measurement is going to say 180. Or you could also turn it in such a way that my next measurement would be 0. I go back to the same number that I started on. The more modern approach to this, and I would hope that the instrument gets into it, or the book does, and I'm not quite there yet, but I'll just skip ahead and tell you the process. This scope right here in the middle is made by a man, or a machine that was made by a man, and it's put in place, and it may not be perfectly correct. So what you do is you turn your first angle, and this is where if we were in person, I'd show you an instrument and it would be very easy to understand. Turn your first angle and you record it. And then you take this scope and you turn it upside down so it's pointing the other direction. And then you turn the angle again and you take a measurement. And what that does is it eliminates any error that was in the placement of this scope. By flipping it over and taking it again, you have corrected any error, which is very important because you want to eliminate as much error as possible when surveying. So flipping that scope over and then following the procedure of doubling the angle will, like I said, remove the error that's built into that scope. This particular display is very similar on total stations, but total stations are going to give you more information. This is a vertical angle. This is your horizontal angle. Bunch of different buttons. It's not a big deal for me to go over this with you because this type of instrument is just about obsolete. It's almost totally been replaced by the total station. Here's just a set of notes, and this is goes back to that diagram we'd seen where we came up short, and you need to be able to equal 540 degrees. And you'll see here we noted we missed it by 1 minute. So you would disperse that equally over every angle to correct its measurements. I'm not really going to worry too much about this. Excuse me, I wanted to, that's the human side of this. I wanted to pause everything before I sneezed. So I didn't, and you have me sneezing instead of pausing. So back to the screen share. Hopefully you got a little laugh out of that. This isn't that important other than realizing that an instrument is set up, and it does show you a few parts down here that are somewhat important. I mentioned before about a tribrac. This is right here. These foot screws are still on things today. You adjust these screws. There's usually 3 of them. Older instruments had 4. You adjust these screws. There's 3. There'll be 1 over here in the middle and these 2 on the sides. And you would level the instrument utilizing these, and it's optical plummet. Nobody uses a plumb bob over an instrument anymore. These optical plumbs like this would be centered right over top of the point. You would be able to look through target a piece of glass on the side, and it would have a mirror inside here and reflect down to the bottom. My instrument, along with most of the current instruments, actually have a laser that emanates from the instrument in here and shoots straight down to the ground. And that's what you would use for your center point or your plumb point. The way these instruments work doesn't much matter. This particular thing is called bucking in or interlining. You wouldn't do it too much, but I can tell you, like for example, here's a case how you would actually do this. The way the book describes it, I wouldn't really recommend that in a practical sense anymore. So if you really needed to know the straight line between these 2 points, sorry about that. I wasn't sharing very well. Now I know I'm sharing. So I wanted to go, let me go back. That's a total mess, but I got to go back and just fix you real quick. Here's where the slide was where I was talking about adjusting your angles. And I'm not going to repeat everything, but this is where you came up short each one of these angles and you'd have to add them on. I wanted to point out here that this is the way an instrument is built. Don't worry too much about it. But right here is the tribrac, and these are the leveling knobs I described. And here's where your optical plumb shoots down the middle. Like I said, today we have lasers. There's your level knobs to adjust everything. And that's how that works. You'd think by now I'd be able to get my videos straight, and obviously I didn't do so good. Let's get back to this right here. This is called bucking in. It's not a technique that's utilized too much anymore, and if you do need to utilize it, there's a pretty good way to do it, and not necessarily the way the book describes. Nobody's going to ask you about it on a test, but what you would do is if you need to see a straight line between A and B, you would go up here on top, and in the middle of everything, you would arbitrarily set yourself up. And you would take a shot to A, you'd turn a horizontal angle to B, and you'd take a shot. You would then be able to know 2 distances and an angle in between. Use a little trigonometry, and it's called a resection, and you can find out the other angles of the triangle and the other distance involved here. And then what you would do is you would compute yourself a point that puts you on the straight line, so that when you set up on that point, the new point, and you would be in a straight line between A and B, you could then sight A, turn an angle to B, it should be 180 degrees. You would then flip the scope over and you could check yourself, and if there's any error, you can take half the distance between each one of those to get yourself in the right spot. But that's how you would do it. Much simpler than the way the book describes, and total stations actually allow you to do that type of thing automatically. I don't need to go over this. This is that double centering. No one's going to ask you anything about this. It's not that important. Intersections, I mean, these are things that they're just different techniques. I would just suggest you skim through it in the book. Here you're trying to get like over an obstacle. You can, the way this is set up is you know where you are. You turn an angle and a distance over to here. And at that point you have 2 known points and you would sight this point. So you, anytime you have 2 known points with a distance in between, you turn an angle to a third point, you will be able to calculate As it shows here with the law of sines, you'll be able to calculate this exact location. It'll give you the distance here and here, and you can do it twice to get each side. You totally configure yourself out, and it's a really good tool for sighting something and getting a location when you physically can't get to it. It's called triangulation, is what surveyors refer to it as. And it is very useful, especially something like a radio tower. That's where I've used it the most. I have used it for cell phone towers and radio towers to locate the tops of them when I can't climb up there and get a shot. So here's the same kind of thing for a tree, to go around it on a tree. Today's total stations eliminate this for you from the math. But if you're going to do triangulation like this, total station is not going to help you unless you have prismless technology to take a shot on this point over here. Otherwise, you're going to have to write things down and do some math to figure out the answer to this question right here. What is the value of B? Like I said, this is old style, was turn 90 degrees to offset around something. That's really not necessary anymore, particularly as we get into the total stations. So that was the end of my lecture here on chapter 6. Butchered a little bit. Hopefully you'll get the gist of it, and I will be right back with a chapter 7.